Okay, hi everybody. So last week we were talking about primary pores in different geological units. And just to quickly review what we talked about last week, remember we were talking about primary porosity and then proceeded to discuss it by rock type. Now, if you remember, we first talked about igneous rocks. And the one thing to remember about igneous rocks is that because they cool from liquid magma into a crystalline form, as those crystals grow, they tend to invade any space that might exist in the rock, and you tend to get a rock composed of interlocking crystals. So in general, most have very low porosities, especially the intrusive igneous rocks that cool in the ground under pressure. Now, some volcanic rocks can have significant porosity where gas bubbles are present. But even for rocks like pumice, where you can get up to 70 to 80% porosity, a lot of these gas bubbles are not interconnected. So when these rocks are in the ground and a fluid like water is trying to flow through it, they're just not permeable, even though they are porous. The pores are not connected. So some volcanics can have significant porosities, but tend to have low permeabilities. And again, most of the porosity, the primary porosity, is ability. I can see if I can spell here. The primary porosity is mostly due to gas bubbles. So the second rock type we talked about were the metamorphic rocks. Remember, metamorphic rocks start with a parent rock, typically some sort of sedimentary rock, and then they experience heat, pressure, and fluids. And what we discussed is that the higher metamorphic grades, the ones that experienced more heat, more pressure, more fluids, tend to be the least porous because those factors, heat, pressure, fluids, tends to make grains grow and fill in the space that might be available for growth. So higher, more metamorphic grades typically lead to lower porosities. The interesting thing also about metamorphic rocks is that you can have what's called anisotropic water movement through the foliated metamorphic rocks that tend to occur in regional metamorphic environments. We're talking about slates, phyllites, schist and gneiss. And remember, these tend to have, especially in the slate, phyllites, and schist, tend to have small mica fragments that, because of the pressure, tend to align in a parallel fashion. So if you have water that moves through, it might move very easily along the trend of the grain, but not very easy across the trend of the grain. So water movement may be very fast in one direction and extremely slow in another. And that's what anisotropic means, is that it's not equal in all directions. You might get preferred flow in certain directions because of the alignment of grains and metamorphic rocks. But the bottom line is that most igneous and metamorphic rocks have low porosities, and therefore, unless they are altered by mountain building or some other process that increases the porosity, they tend not to make very good aquifers. So then we moved on to the third rock type, the sedimentary rocks. And in the case of sedimentary rocks, the porosity is usually found in spaces between grains. And these can be significant. In sandstones, you can get upwards of 30% porosity. Even in shales, you can get up to 30% porosity. But in shales, the porosity tends to consist of pores that are very tiny and very difficult for water to move through. And a lot of them are not interconnected because it's such a small, fine-grained rock that these tiny grains easily fit into any available space. So sedimentary rocks tend to have higher porosities than the other rock groups we discussed. Shales, even though they can have high porosity, they can have low porosity too. Shales kind of run all over the place. They can be as low as 2 or 3% and as high as 20%, but they tend to be impermeable because the pores are either too small or not connected enough for water to move through easily. So shales, even though they can be porous, tend to be impermeable. But sandstones and limestones contain good permeability and good porosity. So they contain high porosity and good permeability. And make good aquifers. So when we're talking about finding rocks that will easily transmit groundwater for wells and for other human purposes, it's these sedimentary rocks that we will turn to, and mostly the sandstones and limestones. The vast majority of aquifers in this country and the vast majority of wells penetrate into sandstone and limestone units. Now, of course, there are some areas where the geology is different and you don't have these porous sandstones and limestones. Some areas on the Great Plains of the U.S. are made primarily of shale. So if shale is all you have, then shale is all you have. And what will happen is that drillers will try to go into the most permeable shale units. It still might not be a very good aquifer, but for most folks, hopefully they can extract enough water to maintain a decent standard of living. Other areas, if you go to the central core of the Rockies, it's all metamorphic and igneous rocks, which have very poor primary porosity. So you tend to look for those units that have been fractured through mountain building or contain secondary pores that we're going to talk about next. So again, this is primary porosity, pores that form during the formation of the rock itself. So let's move on to some new material. And what we'll talk about now is what we refer to as secondary porosity, or secondary pore forming processes. And typically, these occur through chemical reactions in an existing rock. And we'll talk about some of these reactions. If you had physical geology or historical geology or even environmental geology, you probably discussed or talked about a few of these, but I want to make sure everybody's on the same page. So let's just go through these, even if you maybe had them in an earlier class. So one of the most important secondary pore-forming processes is a process called hydrolysis. This is one of the primary chemical weathering processes that we have here on Earth. And the reason that it is so important is that it attacks the silicate minerals. And silicates are the most common rock-forming minerals that we have on this planet. So let's basically go back and review silicates so that we can understand the process a little better. So silicates, again, are the most common minerals on Earth. They're the most dominant in our mantle, most dominant on the crust. They're sometimes referred to as the rock-forming minerals because they are so common. Now, the basic building block of all silicates is a pretty simple little molecule called the silica tetrahedron. Now, silica, the term refers to a molecule that consists of the elements silicon plus oxygen. And tetrahedron is a four-sided pyramid. So this is a molecule, looks like a little pyramid, and it consists of silicon and oxygen. So on this next page, let's sort of draw out what this looks like, okay? So this is going to be the silica tetrahedron. And it consists of a tiny little silicon atom in the middle that has a valence or a charge of +4. And it is surrounded by 4 oxygens. This one I'm drawing here with the dots means it's sort of going into the back. Remember, this is a 3-dimensional structure that will look like a little pyramid. So this is surrounded by oxygens. And the charge on each oxygen is -2. Now, if you look at this, it looks like, and I'm terrible at drawing this, but I will give it my best. Yeah, I've already ruined it, but it is a little pyramid shape, okay? So the oxygens make up the corners of the pyramid, and then the silicon's somewhere here in the middle. So that's where we get the term silica tetrahedron. Silica, silicon plus oxygen, tetrahedron, four-sided little pyramid thing. Now, let's tally up the charges. So in the middle, we have a silicon with a +4. And it's surrounded by 4 -2 charges from the oxygen. So a +4, -2, -2, -2, -2 gives an overall charge of -4. So this little silica tetrahedron has an overall charge of -4. And because things in nature don't really care to have an imbalance with respect to charges, it's going to seek out mechanisms for reducing the charge. So it wants to balance out these charges, and it can do it in a number of ways. If you had mineralogy, you probably saw this more than you ever want to, but even if you had an introductory course, you may have been exposed to this. So we go through a process of balancing charges through, at least in this first example, combining this negatively charged tetrahedron with some positively charged atoms, which are called cations. Cations, again, are positively charged elements. So, give you an example, I think most of you have seen the mineral olivine, a very hard, dense green mineral. Looks like little green sand. The equation for olivine, or one of the, it's actually got a couple different types of chemistry it could display, but one of the simplest forms is Fe2SiO4. So we start out with the tetrahedron that we have near the top here, and basically what you do is you stick in a couple of +2 iron atoms. That balances out the charges. Now, if you repeat this pattern of SiO4 combined with the 2 irons in all different directions, millions of times over, you're going to get a little green olivine crystal. So that is one way we have of balancing the charges, is by combining the tetrahedron with cations. And it could be different kinds of cations. It could be sodium +1. It could be calcium +1. It could be magnesium +2. It could be manganese +2. It could be iron +3. All sorts of different cations. And each of those different cations will bond slightly differently, leading us to different minerals. So in this case, we have an olivine, Fe2SiO4, a really simple little silicate mineral. So that's one way that we can balance charges, is through combining the silica tetrahedron with cations. There's a second way to reduce the charge of the -4 tetrahedron, and that's through a process called polymerization. Now, chemists call polymerization simply the repeating of a chemical group over and over and over again. Basically, what we're going to do here is we're going to make chains and sheets and rows and elaborate frameworks by just combining tetrahedron with other tetrahedron. So follow me here. Let's draw a silica tetrahedron. So remember what was on the other page. A silica tetrahedron, I'm going to draw this right in the middle of the page of notes here, has a tiny little silicon atom with a +4 charge in the middle. And then it has 4 oxygens, each of which has a charge of -2. Okay? And if you remember, add up all of these charges, you have an overall charge of -4. Now, in the previous example, we balanced out that -4 by adding 4 positive charges through the addition of 2 +2 iron cations. Well, there's another way to reduce the charge, and that's by polymerizing or by repeating this pattern that we see with the silica tetrahedron. So basically what's going to happen to this tetrahedron is that each of these corner oxygens are going to be shared with another tetrahedron. So in this case right here, perhaps we will have another tetrahedron right here, where Si +4, and then we've got another O that comes off there, another O that comes off there, and then another O going back here. So now this, I'm going to make it green, this corner oxygen is shared with 2 molecules, that molecule and this molecule. We can do that with this corner oxygen as well. It can be shared with a silicon that has a +4 charge, as well as another oxygen here, another oxygen here, and another oxygen here. So now this oxygen is being shared with 2 polymerized molecules. We can do it again. We can do it with this oxygen right here, Si +4. Let's do an oxygen there, oxygen there, oxygen there. And as you can imagine, we can do it with this top silicon as well. Oxygen there, and oxygen there. So now if you look, each of these corner oxygen in our original silica tetrahedron are being shared with others. Well, when you share an element like oxygen, you also end up sharing the charges. So you can see these charges on each oxygen is -2. Well, each of those oxygen are being shared with 2 silica. So as it turns out, the charges must be shared as well. So if we take, let me get rid of these green marks for a second. Let's say we take this oxygen right here that I'm going to use purple, okay? So that is being shared with this silicon on the right and this silicon on the left. Not only is the atom being shared, but the charge must be shared. So effectively, the silicon on the right gets a -1 charge, and the silicon on the left gets a -1 charge. And if you do that for each of these oxygen, what is the net charge on this particular tetrahedron? Well, it gets a -1 from that oxygen, a -1 from that oxygen, a -1 for that oxygen. It then shares the other charge with the adjacent tetrahedron. Now add these up. -1, -1, -1, -1. That makes -4, which happens to balance out perfectly with the +4. So in this case, you simply have silicon and oxygen, and if you share all the corners, the charges reduce to a point where it's neutral. So bottom line, silicates can reduce their charges on their basic building block, the silica tetrahedron, by bonding with positively charged cations or by sharing their corner oxygen, okay? So that is a silicate mineral. This particular mineral that I drew here, remember we have an Si in the middle, 4 oxygens surrounding it, but remember, because all of the corners are shared, this molecule only receives sort of half credit for these oxygen. This becomes SiO2. This is our mineral quartz. So quartz is nothing but tetrahedron. That's all it is. Now some, and in fact most, silicate minerals are a combination of both of these processes. it will have some corner oxygen shared, but not all of them. So that will leave a net charge of maybe +1 or maybe +2 or maybe even +3. So for most silicate minerals, you have a combination of one or more corner oxygens being shared, along with sticking a cation or two in there. So if you look at the feldspar minerals, it's a combination of corner oxygens being shared along with, let's say, potassium in the case of potassium feldspar, or maybe calcium in the place of plagioclase. Same for the micas. In the micas, the tetrahedron are arranged in a way that they share oxygens on 3 corners to make a big sheet. But one of the corner oxygens then isn't shared. And things like sodium and potassium go in there and can give us things like muscovite. So the arrangement of the tetrahedron along with the cations determines which mineral type we have. So moving forward, getting back to what we were originally talking about, porosity. Now, most of these silicate minerals have very strong bonds. The bonds holding these tetrahedron together are extremely strong. The bonds that hold the cations in are extremely strong. And in fact, that's why magmas are so hot. Magmas are melted silicate minerals, and in order to melt them, you have to have an awful lot of heat. You typically have to raise the temperature of the rock to nearly 1,000 degrees C to get these strong bonds to break. So these bonds are not easily broken. But we do have a process called hydrolysis that I referred to just a little while ago. And it is one of the only ways we have in nature to break down these very tough igneous minerals. And in breaking them down and starting to weather them, you can start to create pores that can allow water to move through your rock. So hydrolysis is the process of taking hydrogen, H+, from water to replace cations in your silicate mineral. And I'll give you an example here in a second. So let's start with water. You guys all know the formula for water. It's H2O. So if you look into your water, and you're able to look at it at the chemical level, you'd see it's made of 2 hydrogen and 1 oxygen. But what happens in nature is that water molecules, especially in liquid water, they move around and they collide with other water molecules. And sometimes they collide with enough energy and at just the right angle that it will break this water molecule apart into an OH minus and an H plus. Now these two species, OH minus and H plus, they have charges. And out in nature seeks to reduce charges. So what typically happens is they recombine to form H2O. And then H2O collides with another H2O and it breaks apart into OH and H plus. And then these recombine, and this constant process of water molecules breaking apart. So bottom line is that if you had a glass of water, the vast majority of it would be H2O. But at any point in time, you're going to have a small amount of OH and a small amount of H plus. And if you happen to have acidic waters just means that you have an abundance of H plus. So you get even more H pluses if you are in an area where the water is acidic. So how does this process of hydrolysis work? Well, let's start with a silicate mineral. Let's start with a simple silicate mineral. So we have Si in the middle. Remember, all silicates are made out of this tetrahedron. So let's build a tetrahedron there. Surround that silicon with 4 -2 oxygens. Okay. Now let's make a olivine molecule. Okay. So let's put in an iron here, Fe+2, and let's put in iron here, Fe+2. Okay, so there is our nice little green sand-like mineral of olivine. And if you remember back to your intro labs, olivine is a really hard mineral. It actually has a hardness of 7, which is hard enough to scratch glass. And these bonds are extremely strong. To melt olivine, you have to raise the temperature to almost 1500 degrees C. So these are not easy bonds to break. But hydrolysis can do it. Now, it's not a fast process. It's actually a pretty slow process. It takes a long time to break down olivine and these other silicate minerals. And what has to happen is you need 2 hydrogens. Okay? And these hydrogens come from water. So basically, you surround your silicate mineral with water, which is mostly H2O, but it also contains some H+. But remember, there's not a lot of H+ compared to water. So this process takes a long time to happen because it doesn't happen all that frequently. And what you have to have are both of these H+ collide with that iron with the right amount of energy and the right amount of angle, and the right angle so that it kicks that iron out. Okay, so the H+ replace the iron. Okay, and the same thing happens over here. You have a couple H+, they sort of bounce around, they recombine with the OH, but if you get 2 of them that hits the iron, just the right energy, just the right angle, it's going to kick that iron out. So now you're left with a silicon surrounded by H+. And over time, the H+ might be replaced with a sodium plus or some other element, but the bottom line is you broke apart that crystal structure, and the result is that you turned it to a mineral called clay. So the process of hydrologist is you're basically just using a little piece of the water, the H+, you're combining it with the tetrahedron. You're going to kick out those cations. Once you break that bond, you greatly weaken the structure, and you end up with clay, which is easily eroded away by the water that's already surrounding it. So if you're eroding away material, you have a process for creating pore space. So the bottom line is that in hydrolysis, the H+ from water replaces the cations in a strong igneous mineral, let's say. Could also be metamorphic, but these typically tend to be found in igneous rocks. And turns it to clay. Now, one thing you should note, though, is that hydrolysis does not act on quartz. It doesn't affect quartz at all. That's why if you go to beaches around the world, most beaches are made of quartz, because quartz is a mineral that's pretty much inert to chemical weathering. There's really no chemical process out there that breaks down quartz. The only thing that breaks down quartz is mechanical energy, basically taking a big piece of quartz and banging it together and making a little piece of quartz. But quartz is not going to be affected by hydrolysis. Why isn't quartz affected by hydrolysis? Go back and look a page or two ago in our notes. What is quartz? Well, quartz is all tetrahedron, isn't it? it doesn't have any cations. It doesn't need cations because all of the corner oxygens are shared to the point where it reduces the charge so that cations aren't needed. So there's no cations to replace. Hydrolysis only attacks the cations. It doesn't do anything at all to the tetrahedron itself. So quartz is a really stable mineral because it doesn't have cations and is therefore not susceptible to hydrolysis. So hydrolysis is an extremely important chemical weathering process that can create pores in rocks that typically don't have many pores, such as the igneous rocks and the metamorphic rocks. So hydrolysis, one of the most important chemical weathering agents we have. Now, a second one that's worth covering is a process called carbonation. And carbonation attacks limestones, or our carbonate rocks. So this is a dissolution of carbonates. And we tend to have two primary carbonate minerals. Two minerals commonly found in calcite, dolomite, limestones. Carbonate. So we have two primary carbonate minerals. We have CaCO3. You guys maybe know this as calcite. And there's a slight variation of calcite called aragonite, slightly different arrangement of minerals, but it's all CaCO3. And then we have some dolomites, magnesium carbonate. And these are the most common minerals that we find in our limestone units. So what we have with carbonation, let me draw a little diagram on the next page, okay? So let's just draw the land surface here, okay? There's a little tree. And let's say that underneath we have a limestone bedrock. And our limestone is a mixture of calcite and dolomite. It could just be calcite, it could just be dolomite, doesn't really matter. It's one of those major limestone minerals. So what happens up in the atmosphere is that we have water vapor up in our atmosphere. And sometimes that water vapor condenses into little liquid, hence the L, raindrops. And those raindrops, though, interact with one of our major gases in the atmosphere, carbon dioxide, which is a gas. And what happens is that if they collide in the atmosphere with the right energy, they can produce H2CO3, which is called carbonic acid. This is one of the more common acids that we find in our atmosphere. And it's just from the mixture of water vapor that's then condensed down to a liquid drop, combining with the CO2 gas that's already in our atmosphere. Okay, so we have carbon dioxide mixing with water to form carbonic acid, and that carbonic acid then falls to earth in raindrops, and some of it starts to infiltrate into the ground, And at some point, it'll go all the way down and join, perhaps, the saturated zone at the water table. So there's saturated zone, here's the unsaturated zone, here's our water table, and we have some carbonic acid going down there. Well, one thing we know is that carbonic acid can dissolve limestone. And the process is actually pretty simple. You have CaCO3, calcite. It could be MgCO3. Doesn't really matter. And that combines with the carbonic acid, H2CO3. And what happens is it dissolves out the calcium. So the calcium is basically busted loose, and you're left with two molecules of HCO3 minus. And all of this is sort of carried away in the groundwater. But in the process, you break apart the rock. So really what's happening is you're breaking the calcium out of the rock and putting it into the groundwater. That's the reason why if you drill a well into this area, you're likely to have what we call hard water. Hard water is water that has lots of dissolved calcium and magnesium in it. And the calcium and magnesium are basically broken loose by this carbonic acid. So it's an effective way to break down these, what we call carbonate rocks. Now, what tends to happen is you tend to get most of this carbonation at the water table, because that's where the carbonic acid level is the highest. It hasn't been diluted yet with water from deeper in the saturated zone. So what you tend to get is areas along the water table may become cavernous over time. It can dissolve completely away and leave caverns behind. So the areas along the water table may become cavernous if this process is allowed to react for a long time. And I can give you a really interesting example of this. If you go up to the Black Hills of South Dakota, there are two national parks. There's Wind Cave National Park, and there is Jewel Cave National Park. And the geology of the Black Hills looks something like this, where you've got a big core of igneous rock in the middle, and then you have dipping sedimentary rocks off the side. Okay, so the surface looks like this. So this is igneous rock here in the middle. If I can spell properly. Oh, come on. Let's do this again. Okay, so here, oh, this is just not cooperating with me. All right, so we have igneous rock here in the middle. And then we have sort of dipping sedimentary rocks off to the side like this. And then here's the ground surface there. If you look at the caves in the Black Hills, they are basically all running parallel to the Earth's surface. And what that means is that these caverns that form in these limestone units formed after the uplift of the Black Hills, because these will form along the water table. And it shows that the water table occurred in dipping rock units rather than horizontal rock units. If these caverns had formed before the uplift of the Black Hills, you would expect to see maybe the caves look like this, along a unit where the water table used to be like that before the folding occurred. But they don't. They occur parallel to today's surface, so that means that the formation of these caverns are actually pretty recent. So the Black Hills uplift occurred somewhere between 40 and 70 million years ago during the uplift of the Rocky Mountains. Cave systems there are parallel to present day water table. And it suggests that these caves are pretty recent, since the caves cut across these rock units rather than be confined to a single one. So these are ways of forming secondary porosity. So that's chemical weathering. You can also get secondary porosity through mountain building that fractures rock. So if you have a mountainous area, like here in the Rockies, then even igneous rocks that normally don't have much porosity can be broken in a manner where water can easily flow through it. So let's stop with this chapter, and we'll go on and talk about something else in the next video.